In this explainer, we're jumping right into the fundamental secret of the universe that literally powers our modern technology, electromagnetic induction. Okay, think about the ultimate question here. How do entirely invisible magnetic fields give rise to the actual physical power lighting up the screen you're looking at right now? Honestly, it feels a little bit like magic when you really stop and think about it, but it's actually rooted in some incredibly elegant physics.
Just picture this setup. Simply moving a permanent magnet near a wire coil creates electricity. You can literally see a center zero galvanometer deflect, which proves right there that a current is present. But, and this is the absolute crucial takeaway, it only works as long as the magnet is actually moving. If the magnet stops, the current stops. No change, no power. It's as simple as that.
To get the whole picture, we're going to build a concept tree to map out how this simple physical phenomenon branches out into real engineering. We'll hit the basics, Faraday and Lenz's laws, dynamically induced EMF, self and mutual induction, and finally wrap up with the coefficient of coupling.
Starting with Section 1, the basics of electromagnetic induction. Let's establish the foundational vocabulary we need for this.
The terminology we absolutely have to master right off the bat is flux linkage. This is simply the product of the number of turns in a coil, which we call N, and the magnetic flux, represented by phi or phi. So the key here is that the basic requirement for inducing an electromotive force, or EMF, isn't just that flux exists in space. It's the changing of those flux linkages. You literally have to disrupt the status quo of the magnetic field if you want to get a spark. Moving into Section 2, Faraday and Lenz's laws. Let's formalize this invisible magic into some concrete rules.
Michael Faraday is the absolute pioneer here. His first law basically confirms that core rule we just talked about. Changing magnetic flux induces an EMF. But his second law, that introduces the math. Faraday gives us the how much. He shows us that the magnitude of the induced EMF is directly proportional to the rate of change of the flux linkages. Put simply, the faster you move that magnet, meaning the faster you change that magnetic field, the bigger the electrical push you generate.
But what about the direction of that electrical push? Well, that's governed by Lenz's law, which states that the induced current will flow in a direction to oppose the cause that produces it. This brilliantly illustrates the which direction part of the puzzle. The negative sign in Faraday's formula isn't just a minus. It represents Lenz's law of physical opposition, kind of like a physical rebellion. The universe naturally pushes back against the change you're trying to introduce.
On to Section 3, dynamically induced EMF. Now that we know the rules, let's see how engineers actually apply them by physically moving things around.
This sets up a really clear contrast between two different ways of creating that all-important change in flux. On one side, we have dynamic systems, like DC generators. Here, the magnetic field sits completely still, and the physical wires move through it. But on the flip side, we have static systems, like power transformers. In those, the wire sits absolutely still, and the magnetic field itself is what expands and collapses around it. If we focus on the dynamic side for a second, the exact geometry of how you move the wire is super critical. Compare a conductor moving perfectly straight through a field at a right angle versus one moving at a slanted angle, theta. It shows us exactly why the dynamic formula E equals B LV has to adapt to E equals B LV sine theta. It accounts for velocity direction. You only get maximum generation when you're cutting straight across those magnetic lines.
Section 4, self and mutual induction. Let's look at the static branch, where the wire never moves an inch, but the fluctuating field does all the heavy lifting.
First up is self-induction, where a coil essentially acts on itself. When an alternating current flows into a coil, it creates a magnetic field, right? But since that current is constantly changing, the flux changes too. And paradoxically, that induces an opposing voltage within that very same coil. It's this localized loop where the coil creates a field that then literally pushes back against the current that created it in the first place.
The property that measures this self-opposition is called self-inductance, measured in henries. Now, rather than getting bogged down in calculus, there are basically three distinct ways to calculate self-inductance, and it all depends on what info you have on hand. Whether you know the electrical measurements like EMF and current, the magnetic flux, or even just the physical dimensions of the core and the wire turns, you can figure out exactly how much a coil will oppose a change in current.
But what if we place a second coil nearby? This is where it gets incredibly cool. We get mutual induction. Even if coil A and coil B are totally separated and not touching at all, the changing current in coil A spills its magnetic field right over into coil B. We call this mutual flux. This changing field induces a spark in that second coil without a single physical connection. By the way, this is the exact principle making wireless phone charging possible.
And just like self-inductance, the math for mutual inductance perfectly mirrors our three calculation methods, grounding all this complex theory into standard, repeatable equations. The main difference, instead of looking at a single coil's turns, we factor in the interaction between the number of turns in coil A and coil B.
Wrapping up with Section 5, the coefficient of coupling, we need to measure exactly how efficiently one coil actually talks to its neighbor in the real world.
To measure this efficiency, we use the coefficient of coupling, or K. If you look at the formula, K equals the mutual inductance M divided by the square root of the self-inductances of both coils. What this mathematically defines is simply the fraction of magnetic flux from one coil that successfully makes it over, or links, to the other one.
This concept pulls the physics straight into hands-on engineering. Take radio work, for example. You have to deliberately choose between tightly coupled coils for maximum energy transfer, meaning placing them right on top of each other so K is super high, or loosely coupled coils for specific frequency tuning where they are deliberately spaced apart so K stays low. The actual physical, spatial arrangement completely changes your electrical outcome.
Understanding electromagnetic induction shifts our perspective. We stop viewing electricity as some kind of magic and start mastering it as an incredibly precise tool. It powers massive generators, steps up our transformers, and even charges our devices straight through thin air. And it leaves you wondering, if we can do all this with a changing magnetic field, what other invisible phenomena are just sitting there waiting for us to engineer them next?